At 7:42 a.m. on August 17, 1943, Technical Sergeant James McKenna crouched under the left wing of a P-38 Lightning at Dobadura Airfield in New Guinea, watching his pilot prepare for a mission he probably wouldn't survive. The pilot was Lieutenant Robert Hayes, 23 years old, 6 combat missions, 0 kills. The Japanese had sent 18 Mitsubishi A6M-0 fighters to intercept the morning patrol. Hayes would be flying straight into them. McKenna had been maintaining P-38s for 8 months. He knew the aircraft inside and out. Twin-engine fighter, twin-boom design, fast in a straight line, absolute beast at high altitude. But the P-38 had one fatal problem that was killing American pilots every single day. It couldn't turn with a 0. The 0 was lighter, more agile. It could execute a full horizontal turn in half the time a P-38 needed. In a dogfight, that difference meant death. American doctrine said P-38 pilots should never turn with a 0, never try to outmaneuver them, use speed, use altitude, dive in, shoot, climb out, hit and run. Don't get caught in a turning fight. Hayes had tried that doctrine 5 times. It hadn't worked. The 0s were too smart. They baited American pilots into turns, cut inside their turning radius, got on their tail, shot them down. The 5th Air Force had lost 37 P-38s in the past 6 weeks. Most were shot down after being caught in turning engagements they couldn't escape. McKenna had watched too many pilots die. Good men. Kids, really. They climbed into their P-38s with confidence and came back in boxes. Or didn't come back at all. The training manual said the problem was pilot error. The instructors said these pilots weren't following doctrine, but McKenna knew better. The problem wasn't the pilots. It was the control cables. The P-38's aileron control cables ran through the twin booms to the tail section, then forward through pulleys to the wing control surfaces. The cable system had slack. Not much, maybe 3/8 of an inch at full deflection. But that tiny bit of slack created a delay between stick movement and aileron response. At high speeds, it didn't matter. At low speeds, during hard turning maneuvers, that fraction of a second delay was the difference between rolling inside a 0's turn and getting shot down. McKenna had mentioned this to the engineering officer 2 months ago. The officer said the cable tension was within specifications. Factory tolerances allowed for that slack. Changing it would void the aircraft warranty. Besides, no field mechanic had authorization to modify flight control systems. That required engineering approval from Lockheed, and Lockheed was 7,000 miles away in California. So McKenna did something that violated every regulation in the Army Air Force Maintenance Manual. He took a piece of piano wire from a damaged aircraft, cut it to 6 inches, bent it into a Z shape, and installed it as a tensioner on Lieutenant Hayes' left aileron control cable. The modification took 8 minutes. It added 0.4 pounds of tension to the cable. It eliminated the slack completely. Nobody noticed. The inspection crew didn't check cable tension that morning. They were focused on engine oil levels and ammunition loads. McKenna said nothing. He watched Hayes taxi to the runway, watched him take off, watched the P-38 disappear into the morning sky toward the Japanese fighters. What happened in the next 17 minutes would change how every P-38 in the Pacific Theater flew. The first pilot McKenna lost to a 0 was Lieutenant David Chen, July 9, 1943. Chen had been in theater for 3 weeks. McKenna had worked on his aircraft every morning. They talked about California. Chen was from Sacramento. McKenna was from Long Beach. They had both worked on cars before the war. Chen took off at 06:15 on a fighter sweep over Leh. He came back 2 hours later with 3 bullet holes in his left boom and a story about a 0 that had gotten inside his turn. Chen said he tried to roll out and dive away like the manual said, but the airplane felt slow to respond, like there was a delay between when he moved the stick and when the aircraft actually rolled. The Zero almost got him. Only thing that saved him was his wingman shooting the Zero off his tail. McKenna looked at the bullet holes. They were in a tight group. Perfect deflection shooting. The Zero pilot had led Chen perfectly, had anticipated exactly where Chen's airplane would be. That shouldn't have been possible if Chen had rolled hard and dove immediately. Unless the airplane had delayed just long enough for the Zero to get the lead right. Chen didn't fly again. His aircraft went back to the depot for repairs. McKenna never saw him again. 3 weeks later, he heard Chen had been killed flying a different P-38 over Rabaul. Same story. Caught in a turning fight. Couldn't roll out fast enough. The second pilot was Captain William Morrison. Morrison was a flight leader. Experienced. 11 kills. He knew the P-38 inside and out. Knew its limitations. Flew smart. On August 3rd, Morrison's flight intercepted 8 Zeros at 12,000 feet over Oro Bay. Morrison got 1 Zero on the first pass, came around for another run, 2 Zeros reversed on him. McKenna heard the radio traffic afterward. Morrison tried to roll inverted and split S away, called out that his controls felt mushy. The Zeros stayed with him through the maneuver, shot him down at 4,000 feet. Morrison's wingman said it looked like Morrison's airplane wasn't responding fast enough, like he was fighting the controls. Morrison died in the crash. Morrison's crew chief was a friend of McKenna's, a guy named Rodriguez from Texas. Rodriguez was convinced there was something wrong with Morrison's aircraft. He checked everything after they recovered the wreckage. Engine settings, control surface rigging, cable tensions. Everything was within spec. Nothing wrong with the airplane. The official report said pilot error. Rodriguez didn't believe it. Neither did McKenna. By mid-August, McKenna had watched 17 pilots die. Some he knew well. Most he'd only met briefly while doing pre-flight checks. But he'd worked on all their aircraft, had signed off their maintenance logs, had watched them taxi out, watched them take off. Some came back. Some didn't. The ones who came back told the same story. The P-38 felt slow to respond in hard maneuvering, like there was a slight lag between control input and aircraft reaction. Most pilots thought that was just how the airplane handled. Heavy fighter, big control surfaces. Some delay was expected. But McKenna knew that wasn't normal. He'd felt that delay with his own hands when he worked on the control cables, that tiny bit of slack in the system. He started paying attention to the sound the cables made when he tensioned them during maintenance. There was a specific tone, a sort of low twang when you plucked them. Loose cables sounded different than tight cables. McKenna could hear the difference. Every P-38 on the line had cables that sounded slightly loose, within spec, but loose. He mentioned this to Rodriguez one evening after Morrison died. Rodriguez asked what could be done about it. McKenna said, nothing official. But unofficially, there was a solution. It just required breaking regulations that could get them both court-martialed. The problem wasn't that American pilots didn't know what to do. They knew. Every briefing emphasized it. Every training flight drilled it. Never turn with a Zero. Use speed. Use altitude. Hit and run. The doctrine was clear. The problem was that combat didn't follow doctrine. Lieutenant Robert Hayes had been in New Guinea for 2 months. 23 years old. Farm kid from Iowa. He'd flown 6 combat missions and had 0 kills. Not because he was a bad pilot, because he followed the rules. And the rules kept putting him in positions where he couldn't get a shot. On his 3rd mission, Hayes dove on a Zero from altitude. Built up speed to 400 miles per hour. Came in from the sun like the manual said. Got the Zero in his gun sight. Started to pull lead for deflection. The Zero snap-rolled left and dove. Hayes tried to follow. His P-38 rolled into the turn but felt like it was moving through mud. By the time his aircraft pointed where he wanted it, the Zero was gone. Hayes pulled out, climbed back to altitude. No shot fired. 4th mission was worse. Hayes and his wingman jumped 2 Zeros at 15,000 feet. Hayes got the first burst off. Missed. The Zero reversed hard right. Hayes rolled to follow. His wingman called out 2 more Zeros coming in from above. Hayes tried to roll back level and dive away. The airplane responded, but slowly. just slowly enough that one of the diving Zeros got a 3-second burst into Hayes' right boom. 20mm cannon shells. They didn't penetrate, but they scared Hayes badly enough that he broke off the engagement and ran for home with his engines smoking. Fifth mission, Hayes watched his wingman die. The wingman's name was Lieutenant Thomas Parker, 21 years old, Boston. They'd gone through training together. On August 14th, Parker got separated from the formation during a dogfight over Finchhofen. 2 Zeros got on his tail. Parker tried everything. Rolled hard, reversed, tried to scissor. The Zeros stayed with him through every maneuver. Hayes heard Parker on the radio calling for help, heard the panic in his voice, heard him say his airplane wasn't turning fast enough, heard the gunfire, heard Parker scream. Then nothing. Hayes didn't sleep that night. Neither did most of the squadron. Parker's bed stayed empty. His personal effects got packed up and shipped home. His P-38 was written off as combat loss. The maintenance log noted no mechanical issues. The official cause was pilot error during defensive maneuvering. McKenna had worked on Parker's aircraft the morning he died. Everything was perfect. Engine timing, control surface alignment, cable tension within spec. The airplane was fine. But Parker was dead anyway. And McKenna knew why. That fraction of a second delay in the controls, that tiny bit of slack that the manual said was acceptable, it had killed Parker just like it had killed Morrison and Chin and 14 others. The worst part was the smell. Every morning McKenna worked in the maintenance area, the smell of aviation fuel and hot metal and hydraulic fluid filled his nose. It was the smell of aircraft preparing for combat. Some of those aircraft would come back, some wouldn't, and McKenna would be there the next morning, smelling the same smells, working on more aircraft, watching more pilots walk out to machines that couldn't respond fast enough to keep them alive. On the evening of August 16th, Hayes came to the maintenance area, found McKenna working on his assigned P-38. Hayes asked if there was anything McKenna could do to make the airplane roll faster. Anything at all. Hayes said he didn't care if it was regulation or not. He just wanted a chance. McKenna looked at Hayes, saw the fear, saw the desperation, saw a kid who knew he was going to die if something didn't change. McKenna told Hayes to come back in the morning. He'd see what he could do. McKenna worked alone that night. The maintenance hangar was quiet after 2,300 hours. Most of the crew had gone to sleep. The only sounds were the distant rumble of generators and the buzz of insects against the overhead lights. The air smelled like engine oil and tropical humidity. He pulled the inspection panel off Hayes' P-38 left boom. The metal was still warm from the day's sun. Inside, the aileron control cable ran through a series of pulleys toward the tail section. McKenna grabbed the cable with both hands and pulled. Felt the slack. Maybe 3/8 of an inch of play before the tension caught. His hands were covered in grease and his fingers ached from a full day of maintenance work. But he could feel that slack. Clearly. It was wrong. He knew it was wrong. The piano wire came from a salvaged P-38 that had ground looped 2 weeks earlier. The aircraft was scrap, but McKenna had pulled useful parts before it went to the depot, including a 6-inch piece of high-tensile piano wire from the rudder trim system. He'd kept it in his tool bag without really knowing why. Now he knew. He sat on the hangar floor with the wire and a pair of pliers, bent it into a Z shape. The wire was stiff, fought back against the pliers. His hands slipped twice. Cut his thumb on the second try. The blood made the wire slippery. He wiped it on his coveralls and kept working. Took him 8 minutes to get the bend right. The Z shape would act as an inline tensioner, would add just enough preload to the cable to eliminate the slack. Installing it was harder. The space inside the boom was tight. McKenna had to work with one hand while holding a flashlight with the other. The beam kept moving. Shadows jumped across the cable system. His shoulder wedged against the boom structure. The metal edge cut into his arm. He could feel sweat running down his back despite the night air. He disconnected the cable at the pulley junction. His fingers fumbled with the clevis pin. Dropped it. Heard it bounce somewhere in the boom. Spent 5 minutes feeling around in the dark until he found it. The whole time his heart was pounding. If the engineering officer found him doing unauthorized modifications to a flight control system, he'd face a court-martial, possibly a dishonorable discharge, maybe prison time. But Hayes was going to die if McKenna didn't do something. He inserted the piano wire tensioner between the cable end and the pulley, reconnected the cable. The fit was tight. He had to force the clevis pin through. When it finally seated, he tested the tension by hand, pulled on the cable. No slack. The control surface moved immediately. Perfect. McKenna replaced the inspection panel, cleaned up his tools, wiped the blood off the wire and his hands. Walked out of the hangar at 01:15. The tropical night was humid and still. Somewhere in the distance, he heard aircraft engines. Japanese night raiders, probably. The sound made his stomach clench. He'd just modified a flight control system without authorization, used a non-standard part, violated at least a dozen regulations. If the modification failed during flight, Hayes would crash, and McKenna would be responsible. But if it worked, Hayes might live. McKenna went to his bunk, didn't sleep, watched the ceiling until dawn. At 06:30, he walked to the flight line, watched the crew fuel and arm Hayes' aircraft, watched Hayes walk out for his pre-flight briefing, watched him climb into the cockpit. At 07:42, Hayes took off. McKenna stood on the flight line and watched the P-38 climb into the morning sky, watched it join formation with 16 other aircraft, watched them head northwest toward Japanese airspace. And then all he could do was wait. The engagement started at 08:14. Hayes' flight of 4 P-38s intercepted 9 Zeros at 13,000 feet over the Huon Gulf. The morning sun was behind them. Perfect setup for a diving attack. Hayes was flying number 3 position. His element leader called out the bounce. They rolled in. Hayes picked a Zero at the back of the formation, dove from altitude, built speed to 380 miles per hour. The Zero grew larger in his gun sight. Hayes could see the painted rising sun on the fuselage, could see the pilot's head in the canopy. He pressed the trigger. The 450 caliber machine guns and single 20mm cannon hammered. Tracers reached out. Most missed. A few hits sparked off the Zero's wing. Not enough. The Zero snap-rolled right and dove. Hayes rolled to follow. That's when he felt it. The airplane responded instantly. No delay. No lag. The stick moved and the aircraft rolled immediately. Hayes had never felt his P-38 move like that. It was like the airplane had been waiting for his command and executed it the moment he gave it. He rolled 90 degrees in what felt like half the normal time. Got his nose down. The Zero was right there in his sight picture. He fired again. 3-second burst. The rounds walked up the Zero's fuselage from tail to cockpit. The Zero's engine exploded. Pieces flew off. The aircraft rolled inverted and fell toward the jungle below, trailing black smoke. Hayes' first kill. But there was no time to celebrate. His wingman called out Zeros diving from above. Hayes looked up, saw 3 of them coming down in a shallow dive, coming fast. They'd seen him shoot down their friend. Now they wanted revenge. Hayes shoved the throttles forward, started to climb, but the Zeros were faster in the dive. They'd be on him in seconds. His only option was to reverse and fight. Every instinct screamed at him to keep climbing, keep running. That was the doctrine. But doctrine meant dying today. He rolled hard left, pulled. The P-38 snapped around like nothing he'd ever experienced. The nose came through the horizon. He saw the lead Zero. It was turning to follow him, but hadn't expected Hayes to reverse that fast. The Zero was in a bad position, exposed. Hayes pulled lead, fired, hit the Zero in the left wing root. The wing folded. The Zero tumbled. 2 kills in 30 seconds. The other 2 Zeros tried to scissor with him, alternating turns to force an overshoot. Hayes stayed with them. Every time they reversed direction, his P-38 snapped into the turn instantly. No delay, no fighting the controls. The airplane did exactly what he wanted the moment he wanted it. It was like flying a different aircraft, like someone had removed invisible weights from the control system. 1-0 made a mistake. Reversed too hard, bled too much speed. Hayes got inside his turn. Close range, maybe 200 feet. He fired. Couldn't miss. The 0 came apart. Pieces of aircraft fell past Hayes' canopy. He felt the P-38 shudder as debris hit his right boom. 3 kills. The fourth 0 ran. Hayes didn't chase. He was low on fuel and ammunition. He climbed back to altitude, reformed with what was left of his flight. They headed home. The entire engagement lasted 7 minutes. When Hayes landed at Dobadura at 09:03, McKenna was waiting on the flight line. Hayes shut down the engines, climbed out of the cockpit. His hands were shaking. His flight suit was soaked with sweat. He walked straight to McKenna. Hayes said 2 words. It worked. What neither of them realized was that 6 other pilots had watched Hayes' engagement from altitude. Captain Frank Mitchell saw the entire fight from 15,000 feet. Mitchell was a flight leader in the 475th Fighter Group. He'd been watching Hayes' element engage the Zeros below when he noticed something unusual. Hayes' P-38 was rolling faster than any Lightning Mitchell had ever seen. The aircraft snapped through maneuvers like it weighed half what it should. Mitchell knew every pilot in the theater, knew their skill levels. Hayes was good, but not that good. Something was different about his airplane. After landing, Mitchell found Hayes in the debriefing room. Hayes was still amped up on adrenaline, hands shaking as he filled out the combat report. 3 confirmed kills. Mitchell asked him what was different. Hayes said he didn't know. His airplane just responded better today, faster. Mitchell asked if maintenance had done anything to the aircraft. Hayes said he should talk to Technical Sergeant McKenna. Mitchell found McKenna in the maintenance area 2 hours later. McKenna was working on a different P-38. His hands were black with grease. His coveralls were stained with hydraulic fluid. Mitchell asked him directly, "What did you do to Hayes' airplane?" McKenna looked at him for a long moment, then told him, "The piano wire tensioner, the cable modification, the unauthorized change to the flight control system." Mitchell listened without interrupting. When McKenna finished, Mitchell asked if he could do the same modification to Mitchell's aircraft. McKenna said yes, but Mitchell had to understand the risks. The modification wasn't approved, wasn't tested. If something went wrong, both of them would face charges. Mitchell said he didn't care. He'd lost 4 pilots in his flight in the past month, all caught in turning fights they couldn't escape. If there was something that could help them survive, he wanted it. Regulations could wait. That evening, McKenna modified Mitchell's P-38. Same piano wire tensioner, same installation method. Mitchell flew it the next morning, came back raving about the improvement. The airplane rolled like a fighter instead of a truck, he told his wingman. The wingman told McKenna he wanted the modification too. By August 20th, McKenna had modified 9 aircraft. Word spread through the squadron. Pilots started asking their crew chiefs if they'd heard about the cable modification. Some crew chiefs refused, said it was against regulations. Others were willing to try. McKenna showed them how. Cut the piano wire, bend it into a Z shape, install it as an inline tensioner. Takes 8 minutes, changes everything. The modification spread pilot to pilot and mechanic to mechanic. No official documentation, no engineering approval, just whispered conversations in the ready room and maintenance area. Hayes shot down 2 more Zeros on August 22nd using the modified controls. Mitchell got 3 on August 25th. Other pilots started coming back from missions with kills. The statistics were impossible to ignore. Lieutenant James Watkins was a crew chief with the 49th Fighter Group stationed at Guisap. He heard about the modification from a pilot who'd transferred from Dobadura. Watkins was skeptical, but he tried it on 1 aircraft. The pilot came back from the next mission with his first kill after 8 weeks of combat. Watkins modified 4 more aircraft. Other crew chiefs in the 49th started doing it too. By early September, maybe 40 P-38s in New Guinea had the modification. The engineering officer at Dobadura noticed something was different, but couldn't figure out what. Control cable tensions checked out during inspections, because the crew chiefs removed the tensioners before inspections and reinstalled them afterward. The pilots knew. The mechanics knew. Nobody told the officers. The kill ratio started shifting. In July, American pilots in the Southwest Pacific lost 2 P-38s for every 0 destroyed. In August, it was 1.3 to 1. By September, it was nearly even. Something had changed, but officially, nobody knew what. Then the Japanese noticed. Japanese fighter pilots first reported the change in late August. Flight reports from the 11th Air Fleet mentioned that American P-38s were maneuvering more aggressively, rolling faster into turns, reversing direction more quickly. The reports noted that tactics which had worked reliably for months were suddenly failing. Lieutenant Commander Saburo Sakai was one of Japan's top aces. 64 confirmed kills. He'd been fighting American pilots since Pearl Harbor. On September 3, 1943, Sakai engaged a P-38 over Wewak. He used his standard tactic, drew the American into a turning fight, waited for the P-38 to begin its roll, then snapped his turn back the opposite direction to get inside the American's turning radius. Except the P-38 reversed with him. Sakai had executed this maneuver dozens of times. He knew exactly how long it took a P-38 to roll, knew the timing perfectly. But this P-38 rolled faster than it should have. Sakai barely avoided a head-on collision. The American got guns on him. Sakai had to dive away. He returned to base confused and frustrated. Other experienced Japanese pilots reported similar encounters. The Americans weren't flying differently. They were still using the same tactics, but their aircraft were responding faster. Fractionally, but enough to matter. Enough to disrupt the timing that Japanese pilots had learned to exploit. Japanese intelligence tried to determine what had changed. They examined wreckage from downed P-38s, found no obvious modifications. The aircraft looked identical to the ones they'd been fighting for months. The engines were the same. The armament was the same. Nothing visible had changed. What the Japanese didn't know was that the change was hidden inside the boom, a 6-inch piece of piano wire that looked like original equipment. Even if they'd found it, they might not have understood its purpose. It wasn't a new weapon system, wasn't a new engine, just a minor modification to control cable tension. But that minor modification was killing their pilots. By mid-September, Japanese pilots were losing aircraft to P-38s at rates they hadn't seen since early in the war. The psychological impact was significant. For 2 years, Zero pilots had owned the sky in turning fights. They knew they could outmaneuver anything the Americans flew. That confidence was breaking down. Pilots who used to press attacks were becoming cautious, hesitant. They weren't sure anymore if their tactics would work. The Japanese tried to adapt. Some pilots stopped trying to get into turning fights with P-38s, used hit-and-run tactics instead. But that meant giving up their main advantage. The Zero's strength was maneuverability. Fighting like a P-38 meant fighting on American terms. And the P-38 was faster, more heavily armed, and could take more damage. Other pilots tried to compensate by being more aggressive, closing to shorter range before firing, taking more risks. But aggression without the ability to outturn the enemy just meant dying faster. Several experienced Japanese pilots were killed in September trying tactics that had worked perfectly in July. The fundamental problem for Japanese pilots was that they were fighting an enemy they couldn't see. They knew something had changed, but they didn't know what, and they couldn't figure out how to counter it. You can't develop tactics against a modification you don't know exists. By the end of September, the 11th Air Fleet had lost 38 fighters in combat with P-38s. American losses in the same period were 22 aircraft. The ratio had reversed. For the first time in the Pacific War, P-38s were killing Zeros at a better than 1-to-1 rate. Japanese command ordered pilots to avoid engaging P-38s unless they had significant numerical advantage. That order marked a turning point. The Zero had gone from hunter to hunted. And it all came down to a piece of piano wire that nobody was supposed to install. The modification never became official during the war. The Army Air Force Engineering Command learned about it in October 1943, when a maintenance inspector at Dobodura noticed inconsistent cable tension readings. He traced the discrepancies to the piano wire tensioners, wrote a report, sent it up the chain of command. The report sat on desks for 3 weeks, while officers debated what to do. The modification violated regulations, but it was working. Fighter squadrons using the modification had measurably better kill ratios. Pilots were surviving. The question wasn't whether the modification helped. The question was whether to punish the mechanics who'd installed it without authorization, or quietly approve it after the fact. In November, Lockheed sent an engineering team to New Guinea to evaluate the modification. They tested it, measured the cable tension, calculated the stress loads, ran flight tests. Their conclusion was that the modification was safe and effective. It should have been part of the original design. Lockheed integrated a similar tensioning system into the P-38J model that entered production in December 1943, but McKenna never received official credit. No commendation, no medal, no mention in any report. The official Lockheed documentation attributed the control system improvement to engineering analysis. McKenna's name didn't appear anywhere. Hayes survived the war. He flew 63 combat missions, shot down 11 Japanese aircraft, returned to Iowa in 1945, married his high school sweetheart, had 4 children, worked as a crop duster for 37 years. He never forgot what McKenna had done. Every year on August 17th, Hayes called McKenna to thank him for saving his life. Mitchell also survived. He became a squadron commander, led his unit through the Philippines campaign, shot down 16 aircraft. After the war, he stayed in the Air Force, retired as a colonel in 1963. He told the story of McKenna's modification to every young maintenance officer he supervised, made sure they understood that sometimes the best solutions come from enlisted mechanics who see problems the engineers miss. McKenna stayed in the Army Air Force until 1946, returned to California, went back to working on cars, opened his own garage in Long Beach in 1948. He worked on engines for 42 years. Never talked much about the war. When people asked, he'd say he was a mechanic, fixed airplanes, that's all. In 1991, a military historian researching P-38 modifications found references to the piano wire tensioner in maintenance logs from New Guinea. The historian tracked down McKenna through veteran registries. McKenna was 73 years old by then, still working part-time in his garage. The historian asked him about the modification. McKenna confirmed the story, said it wasn't anything special, just something that needed doing. The historian estimated that the modification may have saved between 80 and 100 American pilots' lives based on survival rate improvements in squadrons that used it. McKenna said he never counted. He just remembered the pilots who came back. Hayes, Mitchell, Watkins, the others. That was enough. James McKenna died in 2006 at age 88. He was buried in Pacific View Memorial Park in California. His obituary mentioned his service in World War II as an aircraft mechanic. It did not mention the piano wire tensioner. Did not mention that he'd changed how American fighters flew. Did not mention that he'd broken regulations to save lives. His garage in Long Beach is still there, different owner now, but on the wall in the back office, there's a faded photograph. A young mechanic in coveralls standing next to a P-38 Lightning. The date written on the back is August 1943, New Guinea. That's how innovation actually happens in war. Not through official channels or engineering committees. Through sergeants and mechanics who see problems, find solutions, and don't wait for permission to save lives. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters. Each one deserves to be remembered. And we'd love to hear from you. Leave a comment below telling us where you're watching from. Our community spans from Texas to Tasmania, from veterans to history enthusiasts. You're part of something special here. Thank you for watching. And thank you for keeping these stories alive.
The chemist stands in the Schkopau plant on a cold morning in March 1943, watching the polymerization tanks bubble and hiss as they transform coal and limestone into something that resembles rubber. Barely resembles it, he would admit in private. The Booners coming off the production line that day would go into tires for Wehrmacht trucks, for Luftwaffe bombers, for the panzers grinding eastward through mud that swallowed machines whole. He knows the numbers. He's always known the numbers. And the numbers don't work. They've never worked. By this point in the war, they never will. What he couldn't know, what none of them could know, was that they were trying to solve a problem that had become mathematically impossible. Not difficult, not challenging, impossible. The arithmetic was brutal and simple, and no amount of German engineering could change it. But to understand how this moment came to pass, how an entire military machine could be brought to its knees by something as mundane as rubber, we need to go back to before the war, to a Germany cut off from the world and desperately trying to build an empire on coal and chemistry. In 1933, when Hitler took power, Germany imported nearly 90% of its rubber from foreign sources, mainly from British and Dutch colonies in Southeast Asia. Rubber plantations in Malaya and the Dutch East Indies supplied over 95% of the world's natural rubber, all of it controlled by powers that would become Germany's enemies. Every tire, every gasket, every seal, every insulated wire in the German military depended on rubber that came from places Germany could never reach once war began. The Nazi leadership understood this vulnerability with unusual clarity. They had lived through the First World War, when the British blockade had strangled Germany's access to raw materials and contributed to the empire's collapse. Hitler himself referenced this experience repeatedly, the spectre of starvation and material deprivation haunting his strategic thinking. In his 1936 memorandum on the four-year plan, he wrote with characteristic bluntness about synthetic rubber production, dismissing cost concerns entirely and demanding immediate mass production. It was, he declared, better to produce expensive tires in Germany than to have no tires at all. The chemical giant IG Farben had been working on synthetic rubber since the 1920s. Their scientists, building on decades of polymer research, had developed a family of synthetic rubbers they called Buna, the name derived from butadiene and natrium, the German word for sodium, which served as a catalyst in early formulations. By 1935, they had created Buna, as copolymer as styrene and butadiene that could, in theory, replace natural rubber in most applications. In theory. The first industrial plant began construction at Schkopau in Saxony in April 1936, designed to produce 30,000 tons of Buna annually. A second plant at Hels near Marl was planned for 15,000 tons. These were ambitious numbers, but they fell desperately short of Germany's actual needs. By 1940, IG Farben's internal calculations estimated that the German economic sphere would require 300,000 tons of rubber annually just to maintain military and essential civilian operations. 300,000 tons. To meet that target, they would need synthetic rubber production at a scale that approached 120,000 to 150,000 tons per year, supplemented by natural rubber imports and stockpiled reserves. Construction of the Buna plants was slow, far slower than the optimistic timetables suggested. The complex chemistry required specialized equipment, specialized workers, and above all, time. The Schkopau plant didn't begin commercial production until March 1937. By 1939, as Germany invaded Poland, domestic synthetic rubber production was barely a trickle, somewhere around 30,000 tons that year, perhaps 40,000. Not nearly enough. So where did the rubber come from in those early war years? The answer reveals the fragility of the entire German strategic position. First came captured stockpiles. When the Wehrmacht swept through Poland, France, Belgium, Holland and Norway in 1939 and 1940, they seized the national rubber reserves of each conquered nation. These were finite supplies, measured in thousands of tons, not the hundreds of thousands that would be needed. They bought time, but only that. Second came the Molotov-Ribbentrop Pact, that cynical arrangement between Nazi Germany and Stalin's Soviet Union that carved up Eastern Europe and, crucially for Germany, opened a supply line to the east. Between 1939 and 1941, the Soviets shipped massive quantities of raw materials to Germany, including rubber imported from India and elsewhere, totaling thousands of tons. Without these Soviet deliveries, German planners later acknowledged, Operation Barbarossa would have been impossible to launch. By October 1940, German rubber stocks had fallen to just 1,400 tons, 2 weeks of military consumption in a mobile war. The Soviets kept the German war machine fueled with the very materials that would later be used to invade them. Third came the blockade runners. German vessels and submarines attempted to slip through the British naval blockade to bring rubber from Southeast Asia, from Japan, from anywhere they could find it. These operations were dangerous, slow, and yielded only marginal amounts, a few thousand tons across the entire war, never enough to matter strategically. By 1941, German synthetic rubber production had reached 70,000 tons annually, still far below requirements. When Operation Barbarossa launched in June 1941, it severed the Soviet supply line overnight. Suddenly, Germany was entirely dependent on its synthetic production, whatever could be squeezed from occupied territories, and whatever the blockade runners could bring through. The situation was manageable, barely, as long as the synthetic plants kept running and as long as German forces continued to capture new territories with their own rubber stocks. The chemists at Schkopau and Hughes worked frantically to increase production. By 1942, the Hulls plant was producing 50,000 tons of Bunas annually. Combined with Schkopau and the other facilities, Germany's total synthetic rubber output reached somewhere close to 100,000 tons in 1943, the peak year. 100,000 tons. It sounds impressive. It was impressive. A remarkable achievement of industrial chemistry and engineering, and it was nowhere near enough. Here's where the mathematics became impossible, where the numbers turned into a wall that no amount of German ingenuity could breach. Germany needed 300,000 tons of rubber annually to sustain its war effort. Let's break down where that rubber had to come from in 1943. Domestic synthetic production, 100,000 tons at absolute maximum, assuming every plant ran at full capacity, which they rarely did due to raw material shortages, equipment failures, and the increasing weight of Allied bombing. Natural rubber imports negligible. By 1943, Allied naval superiority had made blockade running nearly suicidal. Japanese submarines would continue to deliver small amounts until 1945, but we're talking hundreds of tons, not thousands. A few cargo vessels might slip through. One submarine load might be 5 tons, 10 tons, drops in an ocean of need. Captured stocks by 1943, Germany controlled most of Europe, but Europe's rubber stocks had long since been consumed. The Eastern Front still yielded some captured material as the Wehrmacht retreated, but these were one-time seizures from specific battles or territories, not sustainable supply lines. Reclaimed rubber, Germany, like every nation at war, ran massive salvage operations to reclaim rubber from old tires, boots, gaskets, anything that could be melted down and reprocessed. This yielded several thousand tons annually, but reclaimed rubber was lower quality and couldn't replace fresh rubber in critical applications like aircraft tires or high-pressure seals. Add it all together. 100,000 tons of synthetic production, perhaps 5 to 10,000 tons from imports and blockade running, maybe 10 to 20,000 tons from salvage and reclaimed material, whatever could be seized from occupied territories. In the best-case scenario, Germany had access to perhaps 130,000 to 150,000 tons of rubber in 1943, against a requirement of 300,000 tons. The gap was 150,000 tons, minimum. That gap represented 500,000 tires that couldn't be made. It represented thousands of aircraft that couldn't fly because their tires, their seals, their fuel lines couldn't be replaced. It represented tanks that sat immobile, trucks that couldn't move, submarines that couldn't dive, because the rubber components that held them together simply didn't exist. The gap was a mathematical certainty of defeat, written in the production figures of every rubber plant in the Reich. Let's put those numbers in human terms, in the language of the soldiers who depended on this material. A single Panzerreif tank required approximately 200 kilograms of rubber for its wheels, seals, electrical insulation, and other components. That's 200 kilograms, not including the spare parts needed to keep it running. Germany produced around 8,500 Panzerreif tanks in 1943. That's 1,700 tons of rubber just for new Panzerreif production. The Panthers that began rolling off the lines that summer, the Tigers, the assault guns, the half-tracks, the endless variety of armored vehicles the Wehrmacht deployed. A Luftwaffe bomber, a Junkers Ju-88, required even more rubber. Its landing gear alone used massive tires capable of handling a loaded weight of 15 tons at landing speeds. The entire aircraft contained hundreds of rubber components, seals in the hydraulic systems, insulation for thousands of meters of electrical wiring, gaskets in the engines, rubber mounts to reduce vibration, fuel line connections, oxygen system seals. Conservatively, each Ju-88 required 300 to 400 kilograms of rubber. Germany produced over 3,000 Ju-88s and variants in 1943. That's at least 900 tons for just one aircraft type. Then there were the trucks. The Opel Blitz, the standard German military truck, used approximately 100 kilograms of rubber per vehicle, mainly in its 6 large tires, but also in seals, hoses, and electrical components. Germany needed tens of thousands of trucks to keep its armies supplied. And unlike tanks or aircraft, trucks wore out their tires relatively quickly under the brutal conditions of the Eastern Front, where mud, snow, ice, and rough roads destroyed rubber faster than it could be replaced. A truck might need a complete set of new tires every few thousand kilometers in combat conditions. Multiply that by the tens of thousands of vehicles in service, and the rubber requirements became staggering, and we haven't even discussed the soldiers themselves. Each German soldier required approximately 15 kilograms of rubber for boots, gloves, gas mask seals, raincoats, and other equipment. Multiply that by millions of men under arms. Then there was the civilian economy, which still needed rubber for essential services, for medical equipment, for industrial machinery, for the thousands small things that kept a society functioning even under wartime conditions. The German Quartermaster Corps maintained detailed records of rubber consumption, and those records tell a story of slow strangulation. In 1942, the Wehrmacht received allocations that allowed, barely, for continued operations. By early 1943, the allocations began to tighten. Units on the Eastern Front reported tire shortages first, tanks rolling on bare metal wheels, trucks patched together with whatever rubber could be scavenged from wrecked vehicles, aircraft grounded not because of combat damage, but because their tires had worn through and no replacements existed. Colonel General Heinz Guderian, the panzer theorist and inspector of panzer troops, understood the mathematics of rubber better than most. He knew that a mechanized force without tires was simply an expensive collection of metal boxes. In reports throughout 1943, he emphasized the critical nature of rubber supplies, warning that the panzer forces were being bled white, not by Soviet guns, but by the inability to replace worn-out components. The irony was bitter. Germany had developed some of the finest armored vehicles in the world, the Panther and Tiger tanks that terrified Allied crews. But those magnificent machines sat immobile because they lacked rubber parts that cost a few marks to produce. The Luftwaffe faced even more immediate problems. Aircraft tires operated under tremendous stress during takeoff and landing, particularly for heavy bombers. A worn tire didn't just ground an aircraft, it could cause a catastrophic crash on landing, destroying the plane and killing its crew. By mid-1943, Luftwaffe maintenance officers were performing desperate triage, pulling tires from damaged aircraft to keep operational planes flying, retreading tires far beyond their safe lifespan, mixing natural and synthetic rubber in repairs that reduced performance but kept wheels turning. Lieutenant Colonel Helmut Felmy, a logistics officer with Luftflotte 4 on the Eastern Front, later described the rubber shortage as one of the most demoralizing factors for aircrew morale. Pilots who survived combat missions only to find their aircraft grounded by tire failures felt betrayed by their own supply system. The joke became darkly common: we can outfly the Soviets, but we can't out-tire them. The Allied planners knew about Germany's rubber vulnerability. British intelligence, through signals, intercepts, and agent reports, had pieced together the outline of Germany's synthetic rubber industry by 1942. The synthetic rubber plants became priority targets, particularly after the Casablanca Conference in January 1943, when Allied leaders approved the combined bomber offensive with specific target lists. Synthetic rubber production was explicitly identified as a critical bottleneck in the German war economy. On June 22, 1943, the 8th Air Force launched a massive daylight raid against the Hull synthetic rubber plant near Marl. Over 200 B-17 flying fortresses were dispatched to the target, fighting through intense fighter opposition and losing several aircraft to German interceptors and flak. Despite 4/10 to 6/10 cloud cover, the American bombardiers scored direct hits on the aiming point. 1,560 bombs fell on the Hulls complex in a concentrated strike that lasted less than 30 minutes. The raid devastated the plant. Production stopped completely for 3 months. 186 workers were killed, 752 wounded. The complex polymerization equipment, which had taken years to build and calibrate, was smashed. Some sections of the plant were simply gone, reduced to rubble and twisted steel. When German engineers surveyed the damage, they estimated it would take months to restore even partial production. The impact on Germany's rubber supply was immediate and catastrophic. Hulls had been producing 50,000 tons of biomass annually, nearly half of Germany's total synthetic rubber output. Its destruction created an instant shortfall of 4,000 tons per month, 4,000 tons that Wehrmacht quartermasters had already allocated to units across Europe and the Eastern Front. Those allocations simply evaporated. Speer's armaments ministry, which had taken control of most war production by this point, moved with characteristic efficiency to disperse rubber stockpiles and rush repairs to hulls. Forced labor from concentration camps was brought in to clear rubble and rebuild production lines. By late 1943, the Hulls plant had resumed partial operations, though it never again reached its pre-raid capacity. But the damage was done. The 3-month production gap created a cascading shortage that rippled through the entire German military for the rest of the war. The Allies didn't stop with hulls. Schkopau, the other major synthetic rubber plant, became a regular target. The massive lunar chemical complex, which produced both synthetic fuel and the raw materials for rubber production, was attacked repeatedly starting in May 1944. Each raid damaged not just the immediate target, but the entire integrated chemical infrastructure that supported synthetic rubber production. A plant that made styrene gets hit, and suddenly 3 different rubber plants downstream have no feedstock. A power station gets destroyed, and the energy-intensive polymerization process grinds to a halt. By late 1944, German synthetic rubber production had collapsed to a fraction of its 1943 peak. Some accounts suggest production fell below 50,000 tons annually, perhaps as low as 30,000 tons by early 1945. The mathematical impossibility had become a physical reality. There simply wasn't enough rubber to go around. The consequences played out on every front. In Normandy in June 1944, panzer divisions attempting to counterattack the Allied beachhead found themselves immobilized not by Allied firepower, but by mechanical failures caused by worn-out rubber parts. Seals failed in tank transmissions. Electrical systems short-circuited when insulation wore through. Tire failures left vehicles stranded. Field Marshal Erwin Rommel, commanding Army Group B in France, reported to Berlin that his forces were bleeding to death from lack of replacement parts, particularly rubber components. On the Eastern Front, where distances were measured in thousands of kilometers and roads often meant mud tracks that destroyed equipment, the rubber shortage became existential. The Great Soviet Offensives of 1944, Operation Bagration in Belarus and the Vistula Oder Offensive, succeeded in part because German mechanized forces lacked the mobility to respond. Panzer divisions that should have been racing to plug gaps in the line instead crawled forward on improvised wheels or sat immobile, waiting for parts that never came. The Luftwaffe's decline from 1943 onward is often attributed to pilot losses, fuel shortages, and Allied air superiority. All true, but the rubber shortage played its part. Every aircraft grounded by tire problems was one less machine that could contest Allied bombers, one less fighter that could strafe Soviet positions, one less transport that could supply encircled troops. The cumulative effect of thousands of small failures added up to a force that couldn't operate at the tempo modern warfare demanded. Lieutenant Werner Eisenbach, a panzer officer with the 11th Panzer Division, later wrote in his memoir about the surreal experience of abandoning perfectly functional tanks during the retreat from the Soviet Union in 1944 because they lacked the rubber seals needed to keep their engines running. "We had fuel," he wrote. "We had ammunition. We had crews ready to fight. What we didn't have were the 100 small rubber parts that held the machine together." And without those parts, 50 tons of German steel became 50 tons of scrap. The German High Command tried everything to bridge the rubber gap. Reclamation programs became mandatory, with severe penalties for units that didn't recover rubber from destroyed vehicles. Research programs explored alternative materials, compressed paper, treated fabrics, even processed plant fibers. Some of these alternatives worked for low-stress applications. None could replace rubber in the critical uses that mattered most. There was talk, briefly, of a massive synthetic rubber expansion program, new plants that would triple production. The plans were drawn up. Sites were selected. But by 1943, Germany lacked the resources to build such facilities. Every ton of steel, every cubic meter of concrete, every skilled worker was already committed to other critical projects. The Reich was trying to fight a multi-front war while also building wonder weapons, increasing aircraft production, maintaining submarine construction, and holding together an empire that stretched from the Atlantic to the Caucasus. There was nothing left for rubber plants that would take years to build and might be bombed to rubble before they ever produced a single tire. And even if they had built new plants, there was the raw material problem. Synthetic rubber required butadiene and styrene, which in turn required petroleum products or coal processing. Germany's synthetic fuel industry was itself under immense strain, barely able to produce enough gasoline and diesel to keep the Luftwaffe and Panzer forces operational. Diverting coal and petroleum to rubber production meant cutting fuel production. It was a zero-sum game where every choice meant losing somewhere else. The Japanese tried to help, e.g. Farben had shared its Buna technology with Japanese chemical companies before the war, and Japan operated several synthetic rubber plants of its own. But Japan faced its own rubber crisis, its own shortages of raw materials and production capacity. What little they could spare was shipped by submarine in tiny quantities, 5 tons here, 10 tons there, drops in an ocean. Some natural rubber did reach Germany through neutral countries like Turkey and Spain, smuggled through Byzantine commercial arrangements that cost far more than the rubber was worth. Some came from occupied territories in Eastern Europe that had small rubber plantations or stockpiles. But these sources together provided perhaps 5% of Germany's needs. 5%. The mathematics of the rubber crisis extended beyond simple supply and demand. It was embedded in the fundamental strategic miscalculation of the entire German war plan. Hitler and his generals had designed a military doctrine based on rapid mechanized warfare, on tanks and trucks and aircraft moving at speeds that required massive amounts of rubber. They had built an army that depended on mobility, then found themselves unable to provide the one material that mobility required above all others. Consider the Eastern Front in 1943. The Wehrmacht held a front line that stretched more than 2,000 kilometers from the Arctic to the Black Sea. Defending such a line required mobility, the ability to shift reserves rapidly to threatened sectors, to concentrate forces for counterattacks, to withdraw before being encircled. Every one of those movements required vehicles, and every vehicle required rubber. When the rubber ran out, mobility died, and when mobility died, the German position became indefensible. The Soviet Union, by contrast, received massive shipments of rubber from the United States and Britain through Lend-Lease. In the first months after Operation Barbarossa, Britain alone shipped 22,000 tons of rubber to the Soviet Union. American synthetic rubber production, which had been minimal before the war, expanded to over 700,000 tons by 1944. Some of that rubber went to Soviet forces in the form of tires, boots, and other finished goods. The Red Army fought on American rubber, while the Wehrmacht ground to a halt for lack of it. There's a moment that captures the absurdity and tragedy of Germany's rubber crisis. In April 1945, as Soviet forces closed in on Berlin, a German tank crew abandoned their Panther tank, one of the most sophisticated armored vehicles of the war, mounting a powerful 75mm gun, equipped with excellent optics, and protected by sloped armor that could deflect most Allied shells. They abandoned it not because it was damaged by enemy fire, but because a rubber seal in the cooling system had failed, and without that seal, the engine would overheat and seize within minutes of operation. A 10-mark rubber part immobilized a tank that had cost hundreds of thousands of Reichsmarks to build. That Panther sat there, intact and armed, while Soviet T-34s rolled past it into the city. The irony would have been amusing if it wasn't so representative of Germany's entire late-war situation. They had the technical knowledge, the manufacturing capability, the skilled workers to build weapons that were in many ways superior to Allied equipment. What they didn't have, what they could never have after 1943, was enough rubber to keep those weapons operational. By the time Germany surrendered in May 1945, synthetic rubber production had effectively ceased. The plants were bombed, captured, or out of raw materials. The stockpiles were exhausted. Vehicles across Germany sat immobile, their rubber components worn beyond use. In the final battles for Berlin, German forces often fought on foot because they lacked the tires to move their remaining vehicles. After the war, Allied intelligence teams surveyed the German synthetic rubber industry extensively. The United States Strategic Bombing Survey produced detailed reports on the effectiveness of attacks against rubber production. Their conclusion was unambiguous. The destruction of Germany's synthetic rubber industry had been one of the most effective elements of the bombing campaign. More effective, they argued, than attacks on ball bearing plants or aircraft factories, because rubber couldn't be stockpiled as effectively, and its absence paralyzed the entire military machine. Albert Speer, Hitler's armaments minister, was even more direct in his post-war testimony. He told Allied interrogators that the May 1944 initiation of sustained attacks on synthetic fuel and rubber production had been the moment Germany lost the war economically. "The enemy," Speer said, "has struck us at one of our weakest points. If they persist at it this time, we will soon no longer have any fuel production worth mentioning." The same logic applied to rubber. Once the Allies identified the vulnerability and attacked it systematically, there was no defense, no alternative, no way to bridge the gap. The deeper lesson of Germany's rubber crisis goes beyond logistics and chemistry. It reveals the fundamental constraint that geography and resources impose on military power. Germany entered the war dependent on materials it couldn't produce domestically and couldn't access through trade once hostilities began. All the German engineering skill, all the chemical innovation that created synthetic rubber, all the industrial effort that built the Buna plants, none of it could change the basic arithmetic. 300,000 tons needed, 150,000 tons available at best, and that gap represented the difference between a mobile army and an immobilized one. There's a calculation that German logistics officers made throughout the war, a simple equation that determined how many kilometers a Panzer division could advance before its rubber wore out. They called it the tire radius, the distance from supply bases to the front line beyond which the rubber needed to replace worn tires exceeded the rubber needed to maintain the advance. Once you crossed that radius, every kilometer forward made your position weaker, not stronger. By 1943, Germany had crossed that radius everywhere. On the Eastern Front, in Italy, eventually in France. Their armies were advancing or defending beyond the sustainable distance from rubber production. And unlike fuel or ammunition, which could be rushed forward in concentrated bursts, rubber wear was constant, grinding, inevitable. Every kilometer driven wore down tires. Every mission flown degraded aircraft landing gear. Every day in the field deteriorated the rubber seals and gaskets that held machinery together. There was no surge capacity, no reserve that could be drawn down in emergencies. There was only the steady mathematical certainty that the rubber was running out. The chemist at Schkopau, watching his polymerization tanks in March 1943, probably didn't think in these grand strategic terms. He thought about yields and purity, about the quality of the Bunas his plant was producing, about whether this batch would meet the specifications for aircraft tires or if it would have to be downgraded to truck tires or industrial belts. But on some level, he must have known. Every chemist in the German synthetic rubber program knew. They knew the numbers, knew the requirements, knew what their plants could and couldn't produce. They knew the gap, and that knowledge must have been crushing. To work with such dedication, to solve such complex technical problems, to achieve what was genuinely a remarkable feat of chemical engineering, and to know that it wasn't enough, that it could never be enough, that the arithmetic of rubber production had doomed the entire enterprise before it even began. They were solving the wrong problem. The question wasn't how to make synthetic rubber more efficiently, or how to increase yields from the polymerization process. The question was whether a nation without access to natural rubber could sustain a modern mechanized war. And the answer, written in production figures and consumption statistics and the mathematics of supply and demand, was no. In the end, Germany's rubber crisis wasn't just unsolvable by 1943. It had been unsolvable from the beginning, from the moment Hitler decided to wage war against nations that controlled the world's rubber supplies. The synthetic rubber program delayed the inevitable, bought time for early victories, allowed the Wehrmacht to project power across Europe for a few years. But it was always a temporary solution to a permanent problem, a chemical workaround for a strategic impossibility. The numbers never lied. 300,000 tons needed, 150,000 tons available. The difference was measured in immobilized tanks, grounded aircraft, and an army that had built its doctrine on mobility, watching that mobility drain away, one worn-out tire at a time, until nothing remained but the stark arithmetic of defeat.